Hello everyone and welcome back to an L582 modeling and control of electric machines and drives. So last time we used the Thevenin equivalent circuit of the machine to derive the very important torque speed characteristics of the three-phase induction motor. We lined it out with this very important equation to be used, that the motor torque is 3 V Thevenin as a magnitude squared divided by R Thevenin plus R2 over S all squared plus X Thevenin plus X2 all squared. That's all multiplied by R2 over S omega S. Okay? So that is the relationship between the motor torque and the slip, okay? And being a relationship with the slip, that means it's a relationship with the speed, because I didn't know that the slip is a direct translation for the speed, because it's ns minus nm over ns. And being the synchronous speed equals 120 f over p, it doesn't have anything to do with the load of the machine, because it just depends on the number of poles, which is related to the machine's design, and the frequency, which is related to the supply you're applying to the machine's terminal. So the synchronous speed theoretically doesn't change here unless you control it yourself, okay? But it doesn't have thing to do with the change in the load, okay? The change in the load changes the mechanical speed, and that's directly changing the slip. So the mechanical speed and slip are directly related. So if you have a relationship between the torque and the slip, that means you have a relationship between the torque and the speed. Okay, guys? If you try to plot this, it will give you the very famous shape for the torque speed characteristics of the three-phase induction motor, like this. That is the motor torque, and that is the mechanical speed or the slip, whatever you want to plot it against, okay? And it will look like this, okay? Like we said last time, the maximum point here, we call it the pull-out torque, okay? That is the pull-out torque. Sometimes we call it the maximum torque. Sometimes we call it the breakdown torque, okay? They're all giving the same meaning. That means that is the maximum torque that can be done. And the slip corresponding to this value, we call it SPO, the slip of the pull-out torque. That is the value of the slip corresponding to the pull-out torque or the maximum torque. Okay, guys? That means you have two zones here, like we said last time. This zone, we call it the stable zone, because your torque is less than the pull-out torque or the maximum torque. This zone, we call it the unstable, or sometimes we call it the breakdown zone, okay? And that's obvious because, here you're just exceeding the pull-out torque, so the machine is breakdown, okay? We don't need to do this at all, okay, guys? This point here, the torque here is the starting torque of the machine. Why? Because it's basically corresponding to a zero speed. The speed here equals 0, okay? Nm equals 0, and that's the state of the starting. The starting point of the machine starts at a 0 speed. So the torque corresponding to this value is the starting torque of the machine. Okay. On the other hand, this point, which is corresponding to a 0 torque, is basically the speed equals ns. The mechanical speed of the machine equals the synchronous speed directly. Remember when we were talking about the theory of operation and said if the mechanical speed of the rotor reaches the synchronous speed, your torque will be 0, because basically there will be no any relative motion between the mechanical speed, which is the rotor actual speed, and the synchronous speed, which is the speed of the magnetic field of the stator. Okay, so the rotor winding will experience no variation in the magnetic field, and so will not be induced voltage in the rotor, and this will kill the machine's torque. So the point corresponding to a 0 torque means your mechanical speed equals the synchronous speed. That's why this value equals the synchronous speed. Okay, and this corresponds to a slip equal 0, because if the mechanical speed equals the synchronous speed, that means the slip equals 0. Okay, guys? On the other hand, here where the mechanical speed equals 0, the slip equals 1. yeah, again, you know, the slip equals ns minus nm over ns. So the mechanical speed 0, that means the slip equals 1. Okay, that's why I'm saying the horizontal axis here can be the mechanical speed or the slip, so you can just play around with them. Okay, but they're just reversed in direction. So it starts here with a mechanical speed equals 0, the slip equals 1. And while you go in this direction, the speed goes up until you reach the synchronous speed at this point, but the slip goes down until it reaches 0 at the same point. Okay, guys? So here's the whole point about this, is we need to investigate actually how the motor here will just respond to the change in the load. Okay, that is the whole point of studying the torque speed characteristics of any kind of a motor. Yeah, so again, the same thing I told you last time as a reminder, that the motor torque has to equal the load torque plus b omega m plus j d omega by dt. Okay, like we said a lot, that is the motor developed torque. Okay, that's the torque that your motor creates. That is your load torque. Okay, and that is the friction torque, because you need to just have some extra torque to overcome the friction of the mechanical parts. And this j d omega by dt, as we call it, the acceleration, or we call it the inertia torque. Okay, like we said many times, that is a transient torque, only appears if there is a change in the speed, like you see in here, and this happens on the starting period or the stopping period or any period where the speed changes. But otherwise, if you're reaching the steady state, this term does not appear. Okay, so the whole point is your motor has to develop as much torque to overcome the load torque mainly, and a little bit extra for the friction and the acceleration torque. But the friction and acceleration torque are very, very small compared to the load torque, so they can almost be neglected theoretically. So the whole point is your motor torque has to be equal to the load torque or a little bit higher than it. Okay, this curve gives you the capability of the motor, is how much your motor is capable of, but how much actually the motor will develop a torque, it depends directly on your load torque. Okay, so I just draw the load torque on the same axis like this. So if the load torque equals this value, I'm gonna call it T load 1. That means this interaction is your operating point. So I'm gonna call this, so that is we call the operating point. Okay, the intersection between the load torque and your motor torque speed characteristics. That means you start working at this point. If you go here, so this point is your actual speed now, and I'm gonna call it 1. And the slip at this point will be equaling S1. Okay? What happens if your torque has just increased? So that is T load 2. So your load torque has just increased from T load 1 to load 2. It's increase. Okay? What will happen is your operating point will now be here. Okay? If you again go down here to find, so you'll find NM2. And its corresponding slip will be S2. Okay? And you can see it from here that if the load torque 2 is higher than load torque 1, that means your load torque increases, your load actually increases. You know from looking here that the mechanical speed 2 will be less than the mechanical speed 1, and that's obvious because the increase in the load is translated into a decrease in the speed, but the slip increases. S2 is higher than S1. Please don't forget that the axis for the speed and the slip are just reversed. Okay, so the slip starting from here to be small and increases in this direction, while the speed in the other way starts here 0 and increases in this direction. Okay guys, so here's the point I'm talking about. Okay, if your load torque keeps increasing here, you will keep increasing the same thing. Your speed will go down and down until you hit the pull-out torque. So that's the whole point, guys. Look at here. With the increase in the torque in this zone, the speed keeps reducing, like you see in here. until you just hit this point. But after this, what will happen is the torque will start decreasing and the speed was also decreasing. That's what we call breakdown. The machine is losing torque and losing speed because it's basically you're in a breakdown. The winding will start burning and the machine will be just going into breakdown. Okay, that's why we don't deal with this as an actual zone, because you don't really go in there much, otherwise you're burning your machine. So most of the time we're just dealing with this area, the stable zone of the machine. Okay guys, so that is how you actually deal with this. I hope you now understand how actually you can understand this torque speed characteristics and how actually the change in the load is translated into different speeds and slips over here on this torque speed characteristics of the machine. Okay, so if you want to just keep doing with this, you will have a little bit of understanding of what's happened. So let's go back to the equivalent circuit, that is R1 JX1, and here is your JXM, and here is JX2 and R2 over S, and here is V1. Okay guys, here is your stator current I1, here is your rotor current I2, and here is IM, which is the current goes to XM. Okay guys, during the last lectures we've been just dealing with how we find all the equivalent circuit parameters for this. So if you have the equivalent circuit parameters R1, X1, R2, X2 and XM, now you can use this to find whatever you want on the calculations of the machine. So the very first one, if you want to find here the starting current, okay, I1 starting, the starting current of the machine. Okay, and for you to know the starting current of the machine, like we said before in different kind of machines, even in DC machines and all the stuff, that the starting current is much higher than the running current. So the machine at the very beginning just draws a very high amount of current compared to just while it's running. And we said this before, if you remember, that is the machine's current I1 basically will equal V1 minus E, which is the induced voltage, divided by some sort of an impedance. Okay, I'm not talking here about specific impedance of the stator or the rotor, but it's a very general equation for any kind of a machine, because you're talking about just a coil, which is the stator coil here with the current moving inside this coil. Okay, at the starting, this equals 0, the induced voltage. Why? Because it just depends on the speed all the time. If you remember, E equals BLV. V is the speed. Okay, so at the starting the speed equals 0, that means the induced voltage equals 0, and that means now the current at the starting will equal just V1 over Z, and that's a very high amount compared to the running condition. Okay, that's a general thing you'll encounter in most of the machines you'll be seeing. What about here? How you can calculate the starting current for a three-phase induction motor using the equivalent circuit? It's very easy. To find the starting current, just easily the starting case of the machine, that means the mechanical speed equals 0, because at this instant the machine does not, or just didn't rotate yet. Okay, so the speed equals 0. That means your slip equals 1. So easily just place this slip to equal 1 on this equivalent circuit and just solve to find I1, and this will be your starting current. You solve to find I1 and this will be your starting current. That easy. Okay, and that's why I'm saying here in the running condition, guys, the slip is very small, like we've seen before. For running condition, the mechanical speed is very close to the synchronous speed, and that means the slip is very small. Like we said before, it will be like 0.02, 0.03. That's why for the running condition, R2 over S will be very high, and that means the total impedance in this circuit here will be high, and that means if you just divide V1 by this impedance to find the current, it will be just small value. But if the slip equals 1, and the slip, like we've seen here, is in the numerator of R2 over S, so R2 over S will be just a very, very small value compared to the running condition. So the total impedance of the machine here will be very small, and that's why I1 will be just much higher. Okay, guys? That's how you understand this. In the running condition, okay, doesn't look good. Yeah. In the running condition and in starting condition. Okay. So for the running condition, the slip is very small. Okay. So being very small slip, that will lead you to R2 over S to be very high. Okay. That is very high value, and that means the total impedance, the total of the machine, will be very high. Okay, and you just calculate I1 to be V1 over the total impedance of the machine. Okay, if this value is very high, this will be small, and that is the running condition of the machine, and that's how you just see it. Okay. What about the starting condition of the machine? S equals 1. That means R2 over S is very small. So the total impedance, the total, is very small. So if you just want to calculate I1 again, which is V1 over Z total, now this Z total is very small. That means this current will be very high. And that just tells you why the starting current is very, very high here, guys. So that's the whole point. You want to calculate the starting current, just get your equivalent circuit with all the parameters have from your experimental work or given in a kind of a problem, place the slip to equal 1, and just find the total impedance of the machine using the circuit method. That's very easy. Those guys are in series and then in parallel with XM, and then the total is in series with R1 and X1. So you find the total impedance and just divide V1 by the total impedance to find I1. I hope you don't just forget they are all complex numbers now, so you need to go with the complex mathematics to find I1. Okay, guys? Okay. So that's how you calculate the starting current of the machine. Just placing the slip equals 1 and find the current. Easy as that. Okay? Okay, and just using this also you can find the starting torque. By the way, also using the equivalent circuit. Easy as that. If you just can calculate the current here, you can find the torque. Okay, so if you want to find the starting torque of the machine, you can find it from here. Okay, you just find I2, the rotor current at starting. How? Just again using the equivalent circuit. Okay, you just found I1 starting here by just dividing V1 by the total impedance of the machine. Now use it to find I2, also using your circuit method. Okay, remember I1 goes here and then divided between the rotor impedance here and XM. So you can just use it here easily, okay, to find I2 at the starting. Okay, so if you find I2 at starting, you can find the torque easily to be just the P air gap at starting divided by omega s, which is 3 I2 as a magnitude, which is I2 starting, squared R2 divided by S omega s. Okay, and obviously S here equals 1. Okay, guys? Or you can go directly to the torque speed characteristics here and just place S equals 1. That is your torque speed characteristic. So if you place S equals 1 and calculate everything else, you can just find the torque, which now will be your starting torque also. So that easy. Okay, so the whole point is just you go to find the current or the torque or everything at the starting condition. It's just you use the equivalent circuit just like you can use it with anything else, but you place the slip equals 1, and now everything is being calculated at the starting point. Now it gives you the rotor current and the stator current at the starting point, and also gives you the torque at the starting point, everything here. Okay, guys? Okay. So that is the starting point here. That's your starting torque and how you can deal with it mathematically. But what about the very important pull-out torque? How actually to find this point? How to find the value for the pull-out torque and the corresponding slip at the pull-out torque? Okay, because that is the maximum slip you can hit. That is corresponding to the maximum torque you can hit before the machine starts breaking down. Okay, guys? That's very, very important to determine for any kind of a machine, and that will be just our next thing. So we need to find the pull-out torque, T pull-out, okay? And we need to find the slip at the pull-out torque, okay? We call that the slip at pull-out torque, okay? And this obviously is the pull-out torque itself, okay? How to just find those? To find this, I'm gonna take you back to the Thevenin equivalent circuit of the machine. Remember, that is R Thevenin and that is JX Thevenin, and that will be connected directly to the rotor circuit, JX2, and that is R2 over S, okay? Here is your V Thevenin. Again, back to your circuit courses, the pull-out torque can be just translated here, the state of pull-out torque happens when the maximum power is transferred to the rotor side. Okay, it's physics, it's just how much torque. So you're just trying to find the biggest torque that the machine can develop, and that's actually because the torque is mainly is just representing the power that's converted into mechanical energy. Okay, so that means the maximum power that can go to the rotor side from the stator side. Okay, guys, that is your rotor side on this side. That is your rotor side here. Okay, and the power is going to the resistances. So that means we need to find the maximum power that go into R2 over S. That means you want to find the maximum power going to R2 over S. Okay? How to find this? Easily. That can be found using the maximum power transfer theory. Okay, we go back again to your circuit courses. You had a theory called the maximum power transfer, and by the way, that is one of the very, very big beauties about this course and studying induction machines and studying machines at all, is now you actually find out why all the theories you've been dealing with back in your circuit courses. Now you know when can you use Thevenin equivalent circuit with Thevenin theory you have just dealt with before, and how to make benefit of it into a realistic application. And now we're using another theory, which is the maximum power transfer theory you had dealt with before in your circuit courses, but we didn't know why we are using it. So now we know how we can just apply it to the physical application, and you can see it by your own eyes. Okay, guys? So I'm going to use the maximum power transfer theory, which says that for a circuit like that, okay, the value for R2 over S to dissipate the maximum power from this circuit happens only if this R2 over S equals the magnitude of the other impedance of the circuit. The other impedance of the circuit have R Thevenin and X Thevenin X2. So this will give you the magnitude of R Thevenin plus J, X Thevenin plus X2. That is the magnitude of this. That is the maximum power transfer theory. Refer back to your circuit courses if you don't remember this. Okay, guys? So, for the maximum power to go to the R2 over S, R2 over S has to equal the magnitude of R Thevenin plus J, X Thevenin plus X2, which is the rest of the impedance of the circuit connected to your load here, which is R2 over S. Okay, guys? So, if this condition happened, now you are just at the maximum power transfer, and that means you have the maximum torque. So, if this condition is met, that means maximum power transferred to R2 over S, and that means that is the maximum torque, the pull-out torque condition. That's corresponding to this. Okay, guys? So how to find R2 over S as the magnitude of this? Easy. So that is R2 over S here will equal the magnitude of this, which is the square root of the real part, which is R Thevenin squared. Sorry. Have it here. So R2 over S equals the magnitude, or just square root of the magnitude of the real part, which is R Thevenin square, plus the imaginary part, which is X2 plus X Thevenin squared. Okay? This is the condition of the maximum torque, which is the pull-out torque. That means this slip now is the slip at the pull-out torque. Okay? So from here we can find the slip at the pull-out torque to equal R2 divided by the square root of R Thevenin square plus X2 plus X Thevenin squared. That's a very important relationship to keep in your mind. That is the slip at the pull-out torque. Okay? How you find the pull-out torque itself? Simply take this slip at the pull-out torque and substitute in your torque speed characteristics. And this will give you the pull-out torque itself to equal 3 V Thevenin as a magnitude square divided by 2 omega S R Thevenin plus the square root of R Thevenin square plus X2 plus X Thevenin all squared. Okay? So this relationship, just that is how you calculate the pull-out torque, or the maximum torque of the machine. And this again is just by substituting of this value of the slip at the pull-out torque in your regular torque speed characteristics we have just derived back here at the very start. Okay, guys? That is how you can find those guys. Remember, that is your torque speed characteristic, NM and slip. And here is your guy. Those are what you're talking about. That is the slip at the pull-out torque, and that is the value for the pull-out torque itself. You can be just using here. We found this, so derive this again using the maximum power transfer theory. Okay, guys? By the way, for you to know that the pull-out torque is higher than the rated torque of the machine. I'm not saying that the maximum torque of the machine can handle if this is the same like the rated torque of the machine. Remember, The rated value of anything, rated current, rated voltage, rated torque, rated power, is the value that the machine can keep working at all the time without being damaged or even be deteriorated, okay? But the pull-out torque or the maximum torque is a little bit higher than the rated torque, because the machine actually can deliver a little bit higher torque than its rated torque, but for a very short amount of time. Okay, guys? So, to keep in mind that the pull-out torque or the maximum torque of the machine is not like the rated torque of the machine. You can a little bit exceeding the rated torque, and the machine can still handle that, but for a short amount of time. Keep that in mind. But the pull-out torque is at the absolute maximum torque that the machine can deliver. So if you exceed this value, the machine is going into unstable breakdown region. Okay, guys? Okay, and that's why I'm saying here is your stable region, where the actual motor torque is less than the pull-out torque, and that's where you need to keep that. Okay, and here the slip at this point equals 0, and with the increase in the torque here, your slip starts increasing and increasing until it hits the slip of the pull-out torque, which is the maximum value of the slip you can hit, because that is corresponding here to the pull-out torque itself, which is the maximum torque that the machine can deliver. After this, you go into unstable region and the machine started breaking down. Okay, guys? So this slip of the pull-out torque value is very, very important to deal with. Okay? So let me give you a hint here. Look here at the torque speed characteristics of different motors, okay? Or the torque slip. Here is motor number 1. It has a torque speed characteristics like that. I'm gonna call it motor 1. Okay? If you have another motor that is have a torque speed characteristics looks like that, I'm going to call this motor 2. For motor 1 here, that is the pull-out torque of it, of motor 1, and that is the slip of the pull-out torque of motor 1. What about motor 2? Here is your pull-out torque, and here is the corresponding slip of the pull-out torque of the other motor. Okay, guys? For motor 1, that is your stable region, very narrow like that. For motor 2, that is your stable region. See what I'm saying? So, for motor 2 and for motor 1, okay? For motor 2, the slip of the pull-out torque 2 is high. That is much higher than the slip of the pull-out torque of the motor 1. That means motor 2 has much wider stable region. That means it's more preferable here. If you deal with a motor like motor 1 here, guys, that's very, very narrow area to deal with. That means you cannot deal with much intense variation of loads, because if you just have big variation of loads, you can just hit this value and start going into unstable region very easily. But for a motor like motor 2 here, you have a very wide stable region. That means you can deal with just so much variation in loads here, or hold this value before just hitting this and starting going to unstable region. And we like that so much. We like to have higher slip of the pull-out torque, because that means higher stability. Okay, guys? That's a very, very preferable thing. If this is something in your hand, can you actually play with this? Can you design your motor or just do anything with it to make it more stable, to make the slip of the pull-out torque higher or lower? Let's see about this. Okay. So to just learn about this, or how actually we can use this, okay, let us recall back the equation for calculation the slip of the pull-out torque. Okay, so that is the slip of the pull-out torque, which equals here R2 divided by square root of R Thevenin squared plus x2 plus x Thevenin squared. So by looking here, if you want to increase the slip of the pull-out torque SPO, this value, if you want to increase this, so directly you can do this by increasing the rotor resistance R2. Okay? So just by looking at here, so increasing rotor resistance R2 increases the slip of the pull-out torque, and this increases the motor stability. Okay, and that's the whole point about this. But how actually to increase the rotor torque? The rotor resistance R2. How we can increase this? So increasing the rotor resistance actually can take two forms depending on the rotor itself. So for wound rotor type of the machine and for squirrel cage rotor, okay, because we have two types of rotors in this machine. So I'll be talking about a wound rotor machine. To increase this by attaching external resistance, okay, to the rotor winding via the brushes and slip rings. Remember when I just talked about the construction of a wound rotor machine, that your rotor winding actually are just regular wound coils, and you have the terminals of them attached to slip rings, and you have brushes, so you can just actually access the rotor circuit, and that is the very big advantage of the wound rotor machine. So you can increase the rotor resistance by having an external resistance and just attach it to those brushes and slip rings, and now you have a bigger resistance of the rotor, and this will give you a higher SPO, and this will give you higher stability. But what about squirrel cage? Well, you don't have access to the rotor circuit. Okay, for the squirrel cage, the rotor bars can be designed to have higher resistance from the beginning. Okay, so we cannot play with this car cage rotor because it doesn't have any terminals. We cannot access it. But if you need to consider this from the design stage, from the very beginning, you can design it to have high resistance, and that's it. Okay, so we need to increase the rotor resistance as much as we can to increase this. Actually, you can keep increasing it. If you increase the rotor resistance much higher, you even can hit a torque speed characteristic that looks like this. While it's all like you see in here, that is the pull-out torque here. It's the same like the starting torque, because that means this is all your stable region. You don't have an unstable region at all by increasing those resistance that much high. Okay, so problem solved. Increase the rotor resistance as much as you can, and now you have a very wide stable region and don't even have any unstable region. But don't forget, increasing the rotor resistance increases the copper losses in the rotor circuit. Copper losses and rotor, okay? Because you know this. The higher resistance, the more losses you have in, and that means the efficiency of the machine is killed. And that's the whole point. You have to just try to find a compromise between those. Increasing the rotor resistance increases your stability, but it decreases your efficiency. So it's up to you. It's an engineering problem to solve here. Okay, guys, it's not an open way. Everything has a limitation. So you look depending on different application styles, what actually you want from your machine. If you want your machine to be as stable as much because you know that your loads can go much higher uncontrolled, so you just sacrifice the efficiency and increase your root resistance. If your just loads are stable enough and can be predicted all the time, so you don't need to increase the root resistance that much because you don't need that very wide range of stability, so you reduce the root resistance to increase your efficiency. So that's why I'm saying here, you have different ways of designing the machine and operating it for different load requirements and different environments when you just work in the machine at. Okay, guys? For more about that, you have something you need to study it for yourself, and that will be included in your exam, but it is a totally self-study. Okay? If you go to your Doctrinite online material, and I'm gonna just look at it with you here, so you can just type, and you can find this link on detail, but also you can just go and Unite U of C and go to Dr. Andy Knight's personal website, go to machines, and from it pick induction machines, and we know to go to the induction machine standardization. Okay, this page here just going so much about this. So there's the standard of the machine's designing, influence of rotor design on the performance of the machine, and that's what I'm saying here. Okay, so you need to read this yourself. You will have so much very good information about this, how the design of the machine's rotor just influencing your performance depending on what we said here. That's very important thing to find here, the different classes. If you go back to our lectures when we talked about the testing of the machine, and we said for different squirrel cage designs there's different classes. We call it the Nema Classes. The Nema is the National Electric Manufacturers Association. It's a US organization that provides standards for designing the machines like this. So you have 5 different classes of design, like you see in here: class A, class B, class A, B, C, D. So you have just 4 classes. The whole point is it has different slots, or just have different shape for your rotor bars, like we see here in the picture. And with different designs like this, you have different resistances for the bars, and this will control your torque speed characteristics like you see in here. So look at here, you have different torque speed characteristics of the motor depending on the different design of the rotor bar, because those just have different shapes, so those will have different resistances and inductances depending on the design of them, like you see in here. Okay, guys? Like we said, this will just impact the torque speed characteristics of the machine. So, for example, look at class D design, the blue one here, and the torque speed curve. That is what we said about. That's a very high resistance in the rotor, so you have it's all as a stable region. Okay, you have a very high slip at the pull-out torque. But look, for example, at the black one, which is class A, you'll see that it's almost vertical. It's a very narrow, stable region. Okay, guys? And for class B and C, they are different a little bit. For class C, for example, if you can see it here, it will have much higher starting torque. Look at the intersection between the torque speed curve and the vertical axis. That is your starting torque, like you've seen here. So class D has a very high starting torque, and also class C compared to class A and B. Okay, guys? That's what I'm saying here. For class C, you have something that is your starting torque almost higher than the pull-out torque. Okay? That's not the case for the class A, which is a black one, which is the pull-out torque is higher than the starting torque. So if you need a motor with a very high starting torque, but not very high stability, you pick class C, because you have very high starting torque, but the stability region is not very high. If you need one with a very high starting torque and a very high stability region, you go with class D, but you know that class D will have a very low efficiency. Okay, guys? So that's what I'm saying. Read all this. You'll learn so much about how changing the design of the machine will impact the performance. Okay? So that's included in your exam, and it's self-study. So It's one page. You can find it here and look at it. That's very important. And the most important part is just the Nema motor design classes, the different classes for the square cage motor, and how those impact the machine performance, the different torque speed characteristics of them, and whole this. Okay, guys? That's what I said by just, you can, for the square cage rotor, if you want to increase the stability region, you increase the rotor resistance from design. That means you design like class D. See this? That is class D. So yeah, class D, you just have it like that. So you have high resistance. That means you just basically like said. So the rotor bars, you make it like a very small cross-section area like this. It's very small, like you see in here. And this will impact that you have a very high resistance of the rotor, and this will give you a very high stability. But again, it comes with a cost, because the very high resistance is just translated into a poor efficiency. Okay, guys? So again, different designs for different requirements, because as engineers, you cannot expect to have all the benefits. All the time, you benefit something and you sacrifice another thing. Okay, guys? Reading through this will just teach you what are the benefits and the sacrifices for each of those designs, and that's very important to just play or just get your head around them. Okay, guys? Okay. So I'm gonna just leave you a note here that the motor, or yeah, the induction motor standardization page from Dr. Knight's online material as self-study requirement. Okay, guys? And there you can find more information about this stuff by just studying the different design classes of motors, and this will give you different performances depending on the different resistances you can get from this changing designs of this rotor slots. Okay, guys? Okay. So throughout today's lecture, we've been talking about the torque speed characteristics of induction motors, and we've been investigating how actually we can just quantify all these points you can see in here, the starting point here and the pullout point here, and how we can just find everything. And by the way, you can also find the current of the machine at the pullout torque, just doing the same thing. Use the slip of the pullout torque and put it here in the equivalent circuit and just solve the equivalent circuit. Very straightforward. You can find the current at this point and everything. Okay, guys? Because again, all the time we're saying in this equivalent circuit, this value, R2 over S, or the slip value here, is something that translates the loading condition of the machine. So once you know the slip you're working at, and you already know all those equivalent circuit parameters, you can use the equivalent circuit directly to figure out all the values you need. So if you want to find the motor current or the stator current I1 at the pullout torque, just calculate the slip at the pullout torque using the equation we just derived, and place it here in the equivalent circuit, solve the equivalent circuit to find the current, and this will be the stator current at the pullout torque. And also the torque of the pullout torque, of the machine, you can be found using the equation we just derived. Okay, guys? And we just, looked at how to actually derive the slip of the pullout torque and the pullout torque of the machine, and how this be impacting the stability of the induction motor, and how actually you can control the stability range by controlling the rotor resistance for both wound rotor and square cage machine. Okay, guys? That's it. So yeah, thanks so much for joining me today. I hope you found this lecture informative. Take time to go through it and take time to go through this standardization page on Dr. Knight's online material. Both of them are very important and it will give you so much helpful information to understand the performance of three-phase induction motor. Thanks so much guys for joining me today and looking forward to seeing you next time.